Welcome back to this next video in which we are discussing atherosclerosis. Okay, so in this next video what we're actually going to begin discussing is the pathogenesis of atherosclerosis. Now, the model that we are going to discuss is what's called the response to injury model. Now, this is called a model because, of course, all of science is just models to help us understand the reality that we live in. All the physics is just models to help us understand the laws of nature. All the biology, everything is just models of what really is there. Okay, this response to injury model, as it is called, is very widely accepted to mirror the truth of what happens in atherosclerosis. Okay, so there's the title, but understand that this is very widely accepted. So this is, this is a theory. Of course, all science is always just theories, but this is a very good theory. Okay, so don't read the title and think, oh, so is this not true? Is it just a model? Remember, all of science is just models, and this title is just reflecting the fact that this is just a model. Okay, so the response to injury model then. So what actually happens then in the response to injury model of atherosclerosis? Well, the response to injury model of atherosclerosis says that the formation of an atherosclerotic plaque begins with chronic injury occurring to the endothelial cells, and the idea then is that the atherosclerotic plaque that forms is then formed as part of the response to the chronic injury of the endothelial cells, hence why it is called the response to injury model. So let me start by drawing out a little picture of some endothelial cells. So what we're going to do is we're going to go to our artery here. So I'll just bring it back up. And what we're going to do is we're going to zoom in now, and we're just going to show the endothelial cells sitting on their basement membrane with the subendothelial space underneath. Because initially that's the portion that we're going to need to understand atherosclerosis, because as I've told you in the previous video, it's the subendothelial space that is actually going to contain the atherosclerotic plaque. That's where the atherosclerotic plaque is actually going to form. Okay, so let me start then by drawing the basement membrane here, and now let's have the endothelial cells, a few endothelial cells here sitting on the basement membrane. So there's one endothelial cell, and then let's have another endothelial cell here. Okay, and I'll colour in the basement membrane that they're sitting on in green, like so. Oops. Okay, so there would be more endothelial cells, and in fact I feel like I shouldn't just have a hole there, so I will put another endothelial cell here, and of course it will go on and on. So here's another endothelial cell. Now I'm going to have to extend the basement membrane to make it look proper. Okay, so there we go. There are the endothelial cells sitting on the basement membrane. So the idea then is that atherosclerosis is going to occur in the subendothelial space underneath endothelial cells that are being chronically injured. Okay, so what's going to happen is some sort of process is going to lead to chronic injury of the endothelial cells. Now, chronic, remember, means that it's going to be occurring for a long period of time. So over a long period of time, these endothelial cells are going to be continuously injured in some way. So what sort of things can injure endothelial cells chronically? Okay, well, this is where the risk factors for atherosclerotic disease come in. So things like having very high blood pressure, so suffering from hypertension. This is one of the reasons we are so worried about people with hypertension, high blood pressure, because their endothelial cells are going to be chronically injured, and this might then be triggering the beginning of the formation of atherosclerotic plaques. Okay, so hypertension, too high blood pressure, is one of the things that can chronically injure endothelial cells. Also, too high blood glucose level, hyperglycemia, which occurs continuously if you are suffering from diabetes that is poorly controlled. So if you have diabetes, one of the major symptoms of diabetes, in fact the major symptom of diabetes, is that your fasting blood glucose level, the glucose concentration in your blood when you haven't just eaten, is continuously too high. Okay, and this is known as hyperglycemia. And hyperglycemia, one of the reasons it's so bad is that it damages endothelial cells. So the endothelial cells do not like being in too high a glucose concentration. The high glucose concentration in the blood damages the endothelial cells for reasons that are still only just being worked out. Okay, so hypertension, hyperglycemia, which would occur in poorly controlled diabetes. These are both things that could be chronically injuring endothelial cells. Other things which could be chronically injuring endothelial cells are the toxins in cigarette smoke. So when you smoke a cigarette, all of the toxins, you are breathing those in, okay, into your lungs, and then they just cross straight into the bloodstream because, of course, in the lungs, gases just go straight into the pulmonary capillaries and then they're in the bloodstream. So you're breathing in and getting into your bloodstream all of these horrible toxins, and there really are some horrible toxins in cigarette smoke, and these are now in your bloodstream. And if you smoke for a long period of time, you'll be continuously putting these toxins into your bloodstream, and they can damage endothelial cells as well. So smoking is another thing which can lead to atherosclerosis. It's another risk factor for atherosclerosis. So these are all the quoted risk factors, well, some of the quoted risk factors for atherosclerosis: having high blood pressure, poorly controlled diabetes, smoking cigarettes. Another important one is, to add on here, is turbulent blood flow, and this is the most complicated. I mean, these ones are all very simple to understand what they mean, but turbulent flow, what does that actually mean? Okay, so what do I mean by turbulent flow? So basically, there are certain portions of arteries that we acknowledge are particularly at risk of atherosclerosis occurring there, and it's the places where you have junctions. So what do I mean by junction? So if you've got a large artery here, let's say the aorta, with a branch coming off it here, so here's a branch coming off this larger artery. At this branch point, the tissue, the arterial wall, is very at risk of developing atherosclerotic plaques at the branch points. And it's thought that this is because, the blood is flowing in this turbulent way. When blood is going to go down here, it's going to be hitting the blood vessel wall quite hard here. Okay, it's going to be banging up against it there to go down here. So that's what we mean by turbulent flow, this disturbed, strange flow that's occurring at the endothelial cells at these branch points here. Okay, and that's why the branch points are believed to be at particular risk of developing atherosclerosis. So this can also chronically damage endothelial cells. Okay, so those are 4 important things then that can chronically damage endothelial cells. And as I say, these 3, they represent 3 of the huge risk factors for atherosclerotic disease, and therefore all of the consequences of atherosclerotic disease. Okay, so what then does this lead to? How does this then cause the atherosclerotic plaque? Well, these chronically injured endothelial cells, they start behaving in an aberrant way, a wrong way. Okay, and this is called endothelial cell dysfunction. So what the chronic injury is then going to lead to, and I'll draw a nice flow diagram here, is it's going to lead to endothelial cell dysfunction. And we'll just call this endothelial dysfunction. And all this means is that the endothelial cells are going to start misbehaving. They're going to start doing things that they should not normally do. In particular, they're going to start recruiting white blood cells into the subendothelial space. Now that should not happen. Okay, the endothelium should form a nice barrier to things in the blood coming into the subendothelial space. Now that the endothelial cells have been chronically injured in this way, they're going to start dysfunctioning, and they're going to start actually actively moving white blood cells from the bloodstream into the subendothelial space. And this is really why this is called the response to injury model. You see, the endothelial cells have been chronically injured in this way. They're continuously being injured, continuously being hurt. Now, when cells are being hurt, what is the cell's response? Why generally are cells being hurt? Well, if you think about inflammation, when there are infections, let's say, when you have a bacterial infection in some portion of tissue, those bacterial cells are going to release all sorts of nasty toxins which will damage the cells of your body, and the cells of your body then start releasing all sorts of molecules calling for help. Okay, and the idea here is that when the endothelial cells are chronically injured in this way, they're going to believe that it might be that there is some sort of infectious agent, some horrible bacteria maybe, down in the subendothelial space, and they're going to start recruiting in white blood cells, very powerful cells of the immune system, into the subendothelial space to try and help them. So the idea is that the beginning of atherosclerosis occurs when the endothelial cells dysfunction and start calling for help because we believe they're experiencing this chronic injury. Okay, so endothelial cell dysfunction then, they're going to recruit white blood cells. And there are two main types of white blood cells that they're going to recruit. Number one is they're going to recruit macrophages, okay, and number two, they're going to recruit T cells, very powerful cells of the immune system. Okay, so macrophages and T cells are going to be recruited into the subendothelial space by these dysfunctional endothelial cells. Now, the dysfunctional endothelial cells are also going to increase permeability and allow other molecules within the blood to come into the subendothelial space that shouldn't, and we'll discuss that in just a moment. But firstly, let's talk about the recruitment of these white blood cells. So WBCs, by the way, that just stands for white blood cells. Okay, so recruitment of macrophages. So remember, macrophages are these enormous cells which are capable of phagocytosing other cells. So they are capable of phagocytosing bacterial cells, and this is their humongous great role in the immune system for killing bacterial cells. Now, they don't circulate in the bloodstream. Instead, there is a precursor to a macrophage circulating in the bloodstream, which is called a monocyte, okay, which is much smaller, much more condensed. So here is the monocyte circulating in the bloodstream. So I'll colour the monocyte in red here, and I'll label him up. Okay, so this is where shall I label it? Here. So this is a monocyte in the bloodstream, and what's now going to happen is the endothelial cells are going to put on their surface, these dysfunctional endothelial cells that have now decided to call for help because of the chronic injury that they are experiencing. They're going to put on their surface molecules which will bind to molecules on the surface of the monocytes, and these will bind firstly the monocytes onto the surface of the endothelial cells, and then they'll help the monocytes squeeze through the gaps between the endothelial cells. That's very difficult for a white blood cell to squeeze through the gaps between the endothelial cells, because the gaps between endothelial cells are very small, so it's a complicated process, and it requires the endothelial cells to help the white blood cell through. So to do that, the endothelial cells have to put loads of molecules on their surface to help the white blood cells squeeze through that. They also have to change their behaviour to open up the gaps a little bit more. Okay, so what's going to overall happen then is the dysfunctional endothelial cells are going to help the monocytes to cross the endothelium and go into the subendothelial space. Now, if you like, you can learn the great bigger lists of molecules that it is known that the endothelial cells will put on their surface to help the monocytes cross. However, it's not really necessary. For a basic understanding of the pathogenesis of atherosclerosis, we do not need to know all of the different proteins that the endothelial cells put on their cell membranes to actually help the monocytes cross the endothelium into the subendothelial space. We just need to know that these dysfunctional endothelial cells are going to do that. They're going to help the monocytes cross from the bloodstream into the subendothelial space, and when the monocytes do get into the subendothelial space, they will now differentiate into macrophages, which are this much bigger blob of a cell here. Okay, so this is now our macrophage, and we'll discuss what these macrophages are going to do later on. Okay, so this is a macrophage here. A big eater. Right, so that's the recruitment of macrophages then into the subendothelial space. Let's also add on here the recruitment of the T cells, so another extremely powerful cell of the immune system. So we're going to get T lymphocytes or T cells being recruited in as well. So I'll draw a T cell circulating in the bloodstream here. So again, they have a very large nucleus, lymphocytes, and we'll have the T cell shown here in orange. like so. So this is a T cell, and these are also going to now bind to all sorts of different molecules that the dysfunctional endothelial cells have put on their cell surface membrane. These will firstly bind the T cell, so that the T cell is now attached to the endothelial cell, okay, and then they'll help the T cell get through between the endothelial cells and across the endothelium thus. Okay, and by the way, this process where the white blood cells get across the endothelium, between the endothelial cells, that has a fancy name. Where shall I put it? That is known as diapedesis. Okay, so if you hear people talking about diapedesis, it means this process whereby white blood cells are assisted in moving between the endothelial cells to come out of the blood system, to extravasate as it's called. Okay, right, so we're going to diapedese or extravasate T cells as well, and we're therefore going to end up with T cells in the subendothelial connective tissue as well. So here then is our T lymphocyte here. And I'll just label it up. So this is our T cell, and I'll colour him in, of course, in orange as well. Right, so we have now got these macrophages and these T cells coming into the subendothelial space, and again, remember the motivation for this is that these endothelial cells are doing this because they've been chronically injured. That's the whole logic behind the name of this model, as the response to injury model. The endothelial cells have been chronically injured, and they believe that potentially, obviously we don't know what the endothelial cells are thinking, but they believe potentially that there is an infectious agent of some sort in the subendothelial space, and a lot of people are interested in the possibility that maybe there is an infectious agent in the subendothelial space, but that's still very controversial. But certainly the endothelial cells are acting as though there is an infectious agent within the subendothelial space, because they've been chronically injured by these factors here, and they are bringing in macrophages and T cells into the subendothelial space. Okay, so that's part one of endothelial dysfunction. There's another really important part. They are also going to increase the permeability. Okay, so permeability is going to go up. So again, this is all part of the inflammatory response. It's just like the inflammatory response. When you have an infection in a tissue, the endothelial cells are the capillaries of that tissue, not usually the endothelial cells of an artery. The endothelial cells are the capillaries and the post-capillary venules. They do these things. They recruit white blood cells out of the blood's lumen, the lumen of the blood vessel, and into the extracellular fluid. And they also increase the permeability to allow fluid from the bloodstream to get into the extracellular fluid, and the purpose of that is to move all of the plasma proteins into the extracellular fluid, because lots of those plasma proteins are incredibly helpful in killing infectious agents and killing bacteria and the like. Okay, so permeability often does increase in inflammation. And what happens to increase permeability is the endothelial cells contract, and they recoil their peripheral edges to open up gaps that are bigger in between them, so that fluid from the blood can then leave the bloodstream and go into the extracellular space. Okay, so usually they don't open them quite big enough to allow white blood cells to move without having help from the endothelial cells. Okay, but they do increase permeability so that blood plasma and blood proteins in the plasma can move into the extracellular fluid and create us an inflammatory exudate. So again, this is all looking like an inflammatory response is occurring with these endothelial cells. So the permeability of the endothelium increases, and what is one of the important things then that moves into the subendothelial space? Well, we don't care about all the plasma proteins that are going to move. The important thing for our discussion is that LDL is going to move. Okay, so the endothelial cells increase their permeability, and this allows something called LDL, and we will take a moment out now and talk about LDL, but it's going to allow something called LDL to move across the endothelium into the subendothelial space, and these are the key players in the pathogenesis of atherosclerosis. We are bringing in macrophages, we are bringing in T cells, and we are bringing in this thing called LDL. Okay, so We're now going to have a break from the pathogenesis of atherosclerosis whilst we discuss LDL, because this is absolutely essential that we understand this, especially when we come on to discussing the anti-atherosclerotic drugs. LDL is absolutely crucial. So let's take a break and talk about LDLs. We're going to go off with a little bit of a diversion now. LDL. Okay, so what is LDL then? So LDL, it stands for low density lipoprotein. So the L, the first L, is for low, then the D is for density, and then the second L is for lipoprotein. So low density lipoprotein. And these are balls, these are structures that are within your bloodstream. So within your blood, you have low density lipoproteins, and they are made out of lipid and protein, and I will draw you a picture of them, don't worry. And one of the key lipids that they transport is cholesterol molecules. So what I'm going to do before we discuss the structure of a low-density lipoprotein molecule, what I'm going to discuss is what is cholesterol. So we're going to discuss cholesterol first, and then we'll come back to what is low-density lipoprotein. Okay, so I think I'll go over the page to discuss cholesterol. So to explain to you then what cholesterol is, I need to firstly explain to you what a sterol is, and to explain what a sterol is, I need to explain what a steroid is. So I'm going to start off right from the foundations with what a steroid is, and we'll build up to what cholesterol is. Okay, so let's start off then with what is a steroid. So this is something that surprised me when I learned it for the first time. A steroid is a chemical definition. It's not a biological definition. I expected from pop culture's understanding of steroids, the definition of a steroid to be a biological one, it to be a molecule which has incredibly powerful biological activity. Okay, however, that's not the definition of a steroid. Instead, the definition of a steroid is a chemical one. A steroid is a molecule that contains in its chemical structure a certain core chemical structure known as the core steroid structure. So the steroids is a whole class of molecules that all have chemical structures based on a core structure, and what I'm going to do is now show you this core steroid structure. So the core steroid structure is very simple. It just consists of 17 carbon atoms and then loads of hydrogen atoms off those carbon atoms. So I'm going to draw this out in skeletal structure, and remember, in skeletal structure you don't show carbon atoms, they're implicitly shown by the corners of the structure, and you don't show hydrogen atoms coming off carbon atoms. Now this makes the steroid core structure look incredibly simple, because remember, I told you that this structure consists just of carbon atoms linked to other carbon atoms with hydrogens coming off. Okay, so it's going to look incredibly simple when we draw it in skeletal structure, which is one of the main reasons we do use the skeletal structure. So let's begin this. So the steroid core structure then, the 17 carbon atoms are linked up into 4 rings overall. Okay, 3 6-membered rings, like so. So here's the first one and the second one, and then a third one here, and now 1 5-membered ring, like so. Okay, and that's it. That is the skeletal structure for the steroid core structure. Okay, so steroid molecules are molecules whose chemical structures are roughly based on this core steroid structure here. Now, when we're talking about steroids, there's some nomenclature that people often use which helps us navigate our way around this structure. Okay, so each of these 4 rings here is given a name. So this first ring of carbons here is known as ring A, this second ring of carbons here is known as ring B, third ring of carbons is known as ring C, and fourth ring of carbons is known as ring D. Okay, so these are the different names for the rings of the steroid core structure. And we also number up all the carbons of the steroid core structure, so that when we're discussing specific carbons, we all have set numbers for the different carbons. So the way we do this is we begin with ring A here, and we begin with this carbon right at the top of ring A, and we call that carbon number 1. And then we just follow around in a logical way. So we then go to this carbon here, we call that carbon number 2. This carbon here, we call that carbon number 3. This carbon here, we call that carbon number 4. this carbon here is carbon number 5, and then 6, 7, 8, 9, 10, and then we've obviously closed a loop, and then we just go to here, so 11, 12, 13, and then we go down here, 14, 15, 16, 17. So hopefully that now convinces any skeptics that there are 17 carbons in this structure. Now I'll stress again that all of these points are carbon atoms. Where there are missing bonds coming off the carbon atoms, so just picking an odd example here, carbon 15 here, okay, there are 2 missing bonds coming off this carbon, those will be to hydrogen atoms. Okay, so this truly is the skeletal structure then for the steroid core structure. Okay, so I repeat again, a steroid molecule is a molecule whose structure contains something along the lines of this, a molecule whose structure is based on this. So steroids are a huge, great class of molecules. If someone refers to the core steroid structure, they mean this actual molecule. The core steroid is this one. However, very rarely when people say steroid do they actually mean the core steroid molecule, this structure that I've actually drawn out for you. Instead, they are generally talking about the whole class of molecules which have chemical structures based on this. Okay, so steroids, really we are referring to a whole class of molecules with the chemical structure based on this core steroid molecule here. Okay, sterols, it's a similar story. Sterols are an entire class of molecules which all have a structure similar to a core sterol molecule, the structure of which I will show you now. Okay, so sterols are all steroids, and they're steroids which have had an alcohol group added onto a certain carbon. So specifically, we're going to add an alcohol group onto carbon number 3 here. So carbon number 3 is this one here. It's, as you can see, got 2 bonds to other carbon atoms, and then the other 2 bonds will be to hydrogen atoms. What we're going to do is cut one of those bonds to a hydrogen atom and replace it with a bond to an alcohol group, and that will create us the core sterol molecule. So I'll just draw this out here. So here, this is ring A of our steroid structure. This here is ring B of the steroid structure. Here, this is ring C. And then we've got ring D here. And now we're going to put an alcohol group off carbon number 3 there. And that is the core sterol structure. But again, when someone says sterol, generally they do not actually mean this molecule, the core sterol molecule. Instead, they are referring to the entire class of molecules that all have chemical structures based on this molecule. Okay, so sterols are all steroids, but of course not all steroids are sterols. So these are both really classes of molecules. But the actual core steroid and the core sterol, they are just a specific chemical structure, a specific molecule, the molecules that I have drawn here. Okay, so that's what a steroid and that's what a sterol are. Now we're going up another level, and we're going to actually talk about cholesterol, this incredibly important example of a sterol molecule. Okay, so cholesterol, it's going to be a sterol molecule, so its structure is going to be based on the structure that we've got here. Okay, so I'll start by drawing this picture out, and then I'll show you the modifications that we're going to make to that structure in order to turn it into a cholesterol molecule. Okay, so here is ring A then of the steroid structure. Here is ring B of the steroid structure. Here is ring C of the steroid structure. And here is ring D of the steroid structure. We've got our alcohol group coming off carbon 3, and now we're going to make 3 modifications to the core sterol structure to turn it into this specific example of a sterol molecule, which is cholesterol. So change number 1 that we're going to make is we're going to put in a double bond between carbon number 5 and carbon number 6. So going back to our labelling here, this is carbon number 5, this is carbon number 6, so on this diagram here it's these 2. Okay, and what we can see here is that each of these will have hydrogens coming off it. So carbon number 5's got 3 bonds to other carbon atoms, so one of those, the final bond, will be to a hydrogen atom. Carbon number 6 has 2 bonds to other carbon atoms, so the other 2 bonds will be to hydrogen atoms. We're going to take a hydrogen off carbon 3, a hydrogen off carbon 6, and we're going to form another bond between the two. So we're going to turn this bond into a double bond there. So that's modification number 1 that we're going to make to the core sterol structure to turn it into cholesterol. Modification number 2 is we're going to stick 2 methyl groups of carbon number 10 and carbon number 13. So carbon number 10 is here. You can see that it will have 1 hydrogen coming off it. We're going to take that off and we're going to put a methyl group on there instead. And the same is true of carbon number 13. It's got 3 bonds to other carbon atoms, so 1 final bond will be to a hydrogen atom. Cleave that bond off and replace it with a methyl group, and that's the second modification complete. So we're sticking methyl groups of carbon number 10 and carbon number 13, and remember, in a skeletal structure, methyl groups look very simple, they're just drawn like this. And then the most complicated modification we're going to make is we're going to stick an 8 carbon side chain coming off carbon number 17 up here. Okay, and the side chain that we're going to stick on, it looks reasonably nicely symmetric. This is the skeletal structure of it. Okay, so we're counting the carbons: 1, 2, 3, 4, 5, 6, 7, and then 8. So we've stuck this 8 carbon side chain onto it, and that's the third and final modification that we're going to make to this core sterol molecule to turn it into cholesterol. And that structure that you've now got in front of you, that is the structure of a cholesterol molecule. Okay, so the first thing I want to do is just tell you about the naming of the carbons in a cholesterol molecule. So all of the carbons of the core sterol structure, they will keep the same numbering that they had previously, but look, we've added lots of additional carbons on now, so we're going to have to come up with numbers for those as well. So this carbon of this methyl group here, that's called carbon number 18. This carbon of this methyl group is then called carbon number 19. The carbon off this one here is called 20, then we go to this one 21, then to this one 22, then to this one 23, then to this one 24, then to this one 25, then to this one 26, and then down to that one, which is, 27. Okay, so that's the naming or the numbering up of the carbons in a cholesterol molecule. So overall we've now got 27 carbons in a cholesterol molecule. So this is what is meant by cholesterol. It is a specific molecule, and it is very, very lipid soluble. So remember, the reason it will be lipid soluble is, look at this. This is extremely hydrophobic structure. All of the bonds that we've got here are between carbons and hydrogens. Okay, apart from this one little glimpse of a bit of polarity down here in the form of this alcohol group. So all of these are going to be very, very neutral bonds, because carbon and hydrogen roughly have the same electronegativity. So you're not really going to have any polarity, any dipoles here. Okay, so all of this is going to be very, very neutral, and therefore is going to be very lipid soluble and not very water soluble. The one glimpse of polarity that we've got is this alcohol group, where we've got an oxygen bound to a hydrogen and also to a carbon. Now oxygen has a much greater electronegativity than carbon and hydrogen, so it will pull the electrons in those two bonds towards it, and therefore you will end up with a dipole there, where the oxygen will have a partial negative charge and the hydrogen and the carbon will have a partial positive charge. But that's your one glimpse of polarity, and that's the only bit that would be able to interact with water molecules. Okay, so this is cholesterol. Now cholesterol is a very important molecule. We use it in our cell membranes. We use it for making bile salts. The liver uses it for making bile salts, which are extremely important in digestion. We also use it to make steroid hormones. Okay, so it's a very, very important molecule in the body. And basically, LDL molecules are the storage form of cholesterol in the blood. So it's very difficult to transport cholesterol in the blood because, of course, it's very lipid soluble and not particularly water soluble. So instead, what we do is we have to form these structures known as lipoproteins to transport it. Okay, and lipoproteins are made use of elsewhere in the body as well. I mean, this problem isn't just limited to cholesterol. I mean, all fatty molecules, there is the intrinsic problem of how do we transport these things around the blood. Okay, so lipoproteins are the answer. They're a way of transporting fatty molecules around the blood. Now, low-density lipoprotein, the specific lipid that it transports above all other lipids is cholesterol. Okay, so what I now want to do is show you the structure of a low-density lipoprotein ball then. So I'm now going to tell you what is LDL. So LDL is a little ball of lipids and proteins where the principle is that we are going to shield the very hydrophobic portions of the lipids from the actual water of the blood. Okay, so the idea is very similar in fact to cell membranes. So remember back when you studied cell membranes, the phospholipid bilayer, those phospholipids have that polar head. So I'll just draw a basic cartoon of a phospholipid. Remember, the cell membrane consists of a phospholipid bilayer, and I'll just draw a little bit of this, okay, which we usually draw in cartoons like so, okay. Each of these is a phospholipid, okay, like so, and the ball portion here, in orange, this is the polar portion. This is the portion where the phosphate group is. That's the polar portion. This interacts very nicely with water molecules, okay, because it's polar, so it can bind well to water molecules. These two lines here, these are then the hydrophobic tails of the phospholipid. They are not water soluble. They're incredibly lipid soluble. Okay, so these are the hydrophobic portions. So they're long hydrophobic tails. Okay, so these are called the hydrophobic tails. So this is the polar head of a phospholipid, and then these are the hydrophobic tails. So I'll just color code them in. So polar head is shown here in orange, that's the phosphate group. The hydrophobic tails are the huge, great long chain carboxylic acids that are bound as part of the phospholipid structure. So a phospholipid bilayer, the way it works is that you have two layers of phospholipids. Okay, you have one layer where the polar heads are oriented one way, and then underneath it you have another layer where the polar heads are oriented in the opposite direction. And the idea then is that all the polar heads here will face out towards the water. So here, let's say this is the extracellular fluid, so this is the ECF, and this is the intracellular fluid, the ICF here. So the polar heads will then be facing out towards the water, the cytoplasm here, or the extracellular fluid here. So clearly this is the cell membrane, this phospholipid bilayer. Whilst the hydrophobic tails of the phospholipids, they'll be happy as well, because they'll be facing each other, and they're very soluble in each other. They like each other, they aren't binding to each other. Okay, so this is the way then that we create cell membranes. We have the polar heads facing out towards the water, and the lipid tails facing in towards each other. Okay, so remember that important principle, and we're going to use that principle now to create a little ball of lipids that can be soluble within the blood plasma. And the way this is going to work is we're going to have a monolayer of phospholipids where the polar heads will be on the outside facing the water, and then the hydrophobic tails will be facing inwards, and then we'll store the very hydrophobic lipid cargo in the center. Okay, so this is the way an LDL molecule, and indeed all lipoproteins, not just LDL, there are other lipoproteins beyond just the low density lipoprotein, but we'll just discuss LDL, is going to work. You're going to have a monolayer of phospholipids. Okay, and that's the bit that I'm drawing now. So you're going to have a single layer of phospholipids. So rather than a bilayer, you're going to have just a single layer now, where the polar heads will be facing out towards the blood plasma where the water is, and the hydrophobic tails will be facing inwards. So here are the polar heads of these phospholipids, like so, and here are the hydrophobic tails of them facing in towards the center. Okay, so you'll have what's known as a phospholipid monolayer, and it will be in a spherical shape. Okay, so you'll have the surface of a sphere of phospholipids, where their heads are facing outwards and their tails are facing inwards. And as I say, this is known as a phospholipid monolayer. So contrast that to a phospholipid bilayer, which is what cell membranes are like. Okay, now lipoprotein. So it's a ball of lipids and protein. So not only is there going to be a lot of lipid molecules, we've seen lipid molecules already, there needs to be some sort of protein component to this. So also, implanted within the phospholipid monolayer, you have a massive great protein. And in the case of LDL, there is just one protein in the entire LDL molecule, and this is known as the apolipoprotein B100. And for short, this is abbreviated to ApoB100. So the full name for this is apolipoprotein. And the reason it's called apolipoprotein is it means the lipoprotein but without the lipid. Okay, so it's just the protein portion of the lipoprotein. Now, apolipoprotein B100 is the specific and only apolipoprotein that you find in LDL lipoproteins. So in other lipoproteins, you can find loads of different lipoproteins in the phospholipid monolayer of the lipoprotein structure. In LDL, you find one gigantic one, which is the apolipoprotein B100, which is shown here. Okay, so I hope this structure is starting to come together in your head. You have a surface then, a monolayer. The LDL particle is a sphere, and I'll actually give you the diameter of the sphere. It's usually around 25 nanometers in diameter, these things. So an LDL particle is a sphere of diameter around 25 nanometers, and the outer layer of the sphere is made up by a phospholipid monolayer with this massive great protein implanted in it, known as the apolipoprotein B100, and that's the only protein within an LDL particle. Okay, now, that's the core structure, but what was the purpose of this thing, remember? The purpose of this thing was to transport lipid molecules, and the lipid molecule that LDL is specifically going to transport is cholesterol. So what we're now going to do is put cholesterol molecules into this. Now, the normal cholesterol molecules, they can actually be stored in the phospholipid monolayer with the phospholipids because they have this one glimpse of polarity. They effectively have a polar head as well, which is this alcohol group. So they can actually sit in the phospholipid monolayer with the alcohol group facing out. So I'll draw this like so. Here is the alcohol group represented as a red dot there. Okay, and then the rest of the molecule is then extremely hydrophobic, and I'll colour that in blue. So that blue line with a red dot, that's supposed to represent a cholesterol molecule. So also in the phospholipid monolayer, as well as just having the phospholipids, which are part of the core lipoprotein structure, all lipoproteins have to have a protein in there, at least one apolipoprotein in their phospholipid monolayer, and then the rest of the surface is going to be made up of phospholipids. But also in that, in the case of LDL, you're going to have loads and loads of cholesterol molecules also amongst the phospholipids, like so. Okay, so I'll put a phospholipid in between those two cholesterol molecules there, and you can imagine continuing this picture on and putting in lots of cholesterol molecules into the phospholipid monolayer there. In addition, what's going to then be in the core of the lipoprotein? So this is the surface, the phospholipid monolayer of the lipoprotein, the core of the sphere. This is now known as the core of the lipoprotein. What are we going to have in there? Well, we're going to also have cholesterol molecules, but in a modified state. We're going to have what are known as cholesterol esters, which are very simple derivatives of cholesterol molecules. Okay, they can very easily be converted back into cholesterol molecules. So a cholesterol ester, what you do is you take a long-chain carboxylic acid, a very lipid structure, also called a fatty acid, and you esterify it to the alcohol group here. Okay, so you're going to take some long-chain carboxylic acid, and I'll just draw this here. So here's the carboxylic acid head, and here's the R group, and this R group will be incredibly long and incredibly hydrophobic, and you're going to esterify this with the alcohol group. You're going to link it on, and that will destroy the one glimpse of polarity that the cholesterol molecule has, and now it will be truly, completely lipidy. Okay, so now these cholesterol esters are not going to be able to sit in the phospholipid monolayer anymore because they've got a great big lipid molecule stuck onto their alcohol head, which was the only polar portion. So they can't anymore sit in the phospholipid monolayer, so instead they end up sitting in the lipid core. So the lipid core of an LDL particle is absolutely full of cholesterol esters. Okay, so this is why we think of LDL particles then as being these floating stores of cholesterol, because in their core they are absolutely full of cholesterol esters, and in their phospholipid monolayer they have lots of cholesterol molecules free there in there. Okay, so LDL particles are these stores of cholesterol molecules that are within the blood. We're going to have a break here, and in the next video what we'll do is continue on with our discussion of LDL before going back to the pathogenesis of atherosclerosis, because what I want to do is give you a simple overview of how cholesterol metabolism works on the whole body level. Okay, so how cholesterol is put into the blood, how it's taken out of the blood, things like that, because having a basic understanding of that is going to be really important for us to understand how the anti-atherosclerotic drugs are actually going to work. Now, you can learn this to a ridiculous level of detail, and indeed, if you go to my playlist on lipid metabolism, there is a video in there on cholesterol metabolism where I talk about the handling of cholesterol by the body in much more detail than I'm going to in the next video. However, it's not utterly necessary to know that level of detail that's discussed in that video. So I'm going to do a very simple, very brief summary which gets the important points across in the next video. But if you do want the full story, please do go to the video on cholesterol metabolism where we discuss all of the different lipoproteins and how they move cholesterol around.